catalyst for this kind of research, but also pathogen interaction to understand how the actually drive the human genome, and then how we can use such drivers as to actually identify solution, vaccines, and then the candidate. In doing this, we're addressing one of the major critical need, for genomic education and research in Africa, and that critical need is actually genomic capacity building. So by making sure that we set up genomic teaching and sequencing laboratories, diagnostic core facilities, and eventually sustainable science career for young scientists. We're all very much aware in the case of Nigeria of what they call the Japa syndrome. So you got a lot of young people that are fleeing Africa simply because they feel that there's no opportunity, yet, the opportunities are pretty much available. So that's really what we wanted to use this platform to do. So, but ultimately, our goal was actually to build the next generation of African microbe hunters in the dirt roads of Africa by basically just training them on how to characterize pathogens, and then making sure that they hunt and then characterize this pathogen before they come to us. So, and avoid the scenarios that we've gone through by having to respond to so many epidemics, in the past, and then pandemics like HIV and then the COVID-19. So in setting up this platform, I've been very ambitious in doing this. We set this platform in 2013, and then by 2014, we actually were facing our first test. And our first test really was, having that outbreak, or the largest outbreak of infection of Ebola in Africa. And that was the outbreak, the 2014, 2015 outbreak of Ebola in West Africa. But then we seized the moment as well, to actually demonstrate and transform the way outbreak response is being done. And what we did basically at the time was really to look at the landscape and identify the fact that, and recognize the fact that, while Ebola was brewing in the remote confinement of Guinea, not many people thought it was going to spread. We basically recognize the fact that it could spread. And if it could spread, then the question was, what could we do? And then we basically identified diagnostics as the weakest, link of the chain. And as such, we went on to actually train young Africans, especially in the West Africa region, on how to detect, do molecular diagnosis of Ebola, but also how to protect themselves, avoid disease, but also to how to perform genomic sequences. In the first 3 weeks of that outbreak, that spread from Guinea to Sierra Leone, the first week, basically, we identified 35 suspected cases, confirmed 14, but then also did contact tracing to bring down to the index case who was a traditional healer. But then that really, it was just the tip of the iceberg, because we actually went further to actually just made a major transformation on how to respond to the disease, to outbreak in the world. The first thing we did was actually in the first 3 weeks of that outbreak in Sierra Leone, we went on to actually to do what we call near real-time genomic sequencing. That is sequencing the first 99, Ebola genome, and did this at the speed of light. That's to put it at a time. First sequence for the first 99 genomes, made this 99 genome openly available because we wanted the international community to leverage, the genome sequences to actually accelerate vaccine development, drug development, and diagnostic development. So, and then this was basically the first time during an epidemic where you could see scientists, promoting open data sharing, open data access, and then basically just setting up the framework that the world used, in 2019 for COVID-19. So basically, we set up the work, and then set up the framework and save the world from the COVID-19 pandemic, because this was the first time where you could say that sequencing in real time and also share the data in real time can be very helpful and very transformational to develop the countermeasures and protect the world, but also using the data actually to help policymakers and respond to epidemic. We did this, the sequences that I mentioned at the speed of light at the time. Imagine 10 years ago when sequencing was such a very luxury, but we were doing these sequences in 10 days, from sample collection to depositing the data in GenBank. That was a revolution at the time, right? And then we made the data accessible for months before we could have our paper published 9 months later in the journal Science. That really was actually to say open data sharing can actually help to respond to an epidemic. But most importantly is the fact that, if you look at this diagram here, look at this, I will just bring this pointer, look at this date here. June 16, we have 2 different clade or variants circulating in Sierra Leone, but then by June 16, very critical date, then SL3, which is this clade, actually took over and became more transmissible than others. So the question at the time is that what is making this clade more transmission? We realized that the transmission was due to human to sustained by human to human transmission. There was no additional introduction from zoonotic reservoir, and then no newly imported cases from other countries. But then there was something that was very peculiar about this particular variant. And then we went on further to characterize it, and we were demonstrating for the first time in the history of an epidemic that you could have what we call variants of concern that actually transmit much more faster than others. We identified about 371 mutations across the genome of this virus, but then 27 were very fixated and in the places that actually gave the ability of the virus to transmit much more faster than others. So this is the second pillar that we set up, identification and discovery of variants of concern. And you could see, the world leveraging, this approach, for instance, to identify variants of concern during COVID-19 in the world. But then the third thing that we did was basically to see that when you see this transmitting faster than others, how can you use this information to respond to public health? We went on if you look at this diagram, using genomic sequence data to consider the outbreak, identifying hotspots as you see here as they grow bigger, but then having transmission characterized or transmission chain from person to persons, from village to village, from town to towns, from country to countries. And this was the very first time that you could see this kind of approach, for instance, used during an outbreak. With this, we're able to identify the drivers, of this that were fueling this transmission in the region. But by providing this kind of information, we're able to identify the hotspot and then share this information with public health, officials, and then they could use it as a way to respond to and, lock down those areas and then help respond to this epidemic in a way that was unprecedented. But most importantly is the fact that we demonstrated another major pillar here, which is real-time, what we call translational genomics. We knew that we were having challenges in terms of having PCR to be done, over time. It took 72 hours to do a PCR test. People that had malaria fever went to the Ebola Diagnostic Center, got infected there, and yet if they had a test that was fast enough, they could actually test at home to know whether they had Ebola or not and prevent those kind of things. So we went on to actually, use the genome sequence data and translate those genome sequences in creating the first rapid diagnostic test, for Ebola that was approved by the US FDA and then the WHO under emergency use authorization. The introduction of this test, as you see here, was a major game changer because the doctors had, and then the clinicians had the ability to know within minutes what the patient, the type of fever the patient had, whether it was Ebola fever or something else. And this actually was a major game changer that started flattening the curve of this outbreak in West Africa. Then this is another pillar that the world used to respond to COVID-19. You could see the world going from having the genome sequences to create the first diagnostics, the first vaccine within 9 months. So basically, again, show you here, for instance, that the framework that we set up in 2014 is what the world used to respond to the COVID-19 outbreak. Let me fast forward and then to say that, we use the same approach to save Nigeria, a country of 230 million. We had the first case of Ebola in Lagos, a city of 25 million from this, from the epidemic. And we did this in an incredible way. In 93 days, Nigeria contained Ebola outbreak, the epidemic in 93 days with only 20 cases and 8 dead. And this was really driven by a lot of the innovation that we're doing behind, getting information to government in real time, and then showing the world how you could use science and innovation to respond to an epidemic in a way that was unprecedented. I just want to draw your attention to the fact that prior to when we brought these approaches to epidemic response, what used to happen is the fact that, during outbreaks in the past in the DRC and everywhere else in Africa, the WHO will send some so-called experts. They will come in and then take the samples, take them to Germany or to other places in Europe. And it is only maybe a year or two after that will now characterize a pathogen and say, the kind of virus that was infected or responsible to the outbreak in the continent. Let me fast forward to another virus that I'm very passionate about, which is Lassa fever. And this was work I was doing before Ebola. So it's a virus that was described for the first time in Nigeria in 1969. It's American nurses. But then for 37 years, this virus was never diagnosed in Nigeria in terms of molecular diagnosis. So what used to happen that anytime they have outbreaks, then the sample used to be sent to Germany and then analyzed over in Germany. And then eventually, the result come back 3 weeks or a month after when 90% of the people, who were infected have given the ghost. So we went on actually to just decide to actually focus on this virus and then to give it the prominence that it deserves. Because this virus and the disease is actually a neglected tropical disease. In 2007, we actually zoomed our beam, we beam our lenses on this particular virus and went on to actually sequence, the very first virus of this. And when I talk about sequence, I'm talking about whole genome sequences. We provided the whole genome sequences of this virus, and then we went on to sequence hundreds of viruses. Use, molecular clocking, and then we're able to establish, for instance, the ancient origins of this virus. We knew we unraveled the fact that, this virus emerged from present-day Nigeria 1,185 years ago, was circulating in Nigeria for 600 years, moved out of Nigeria 400 years ago toward the western part of Africa. But then we also did here, for instance, using the genome sequence data, we went on to create what we call a pan-Lassa rapid diagnostic test. We determined the fact that, 3 different lineages, variant was circulating in Nigeria. You could see there in different places, 1, 2, and 3, and then the other part of West Africa were being here 4. But we went on to create a pan-Lassa rapid diagnostic test that is actually enable you to differentiate between the different variants that are circulating, and I can get that tested positive. You could see the test here, and then that really was a major game changer. Just want to say that, a disease that was ignored, prior to our work, and then we went on to sequence it. And within 5 years of our sequencing, there were 3 vaccines that actually were ready to be used, and then to undergo clinical trial. As I'm speaking to you, I had to jump off the meeting where we're doing a phase 3 clinical trial of a Lassa fever vaccine in Nigeria, and then other West African countries to join this meeting. But it's just to say that you could see the firepower behind this approach and the technology, and how that can accelerate the development of countermeasures. So with the advent of, gene editing technologies, we actually improve our diagnosis, going from antibody or antigen capture tests, antigen capture tests actually to use gene editing and use a CRISPR as a way to use, the guide RNAs to identify sequences that are unique to every circulating lineage of the virus, cut it, and then eventually have, a reporter that eventually will release your signal, and then you can actually know whether something is positive or negative. I just want to say that, by doing this, we actually produce the very first CRISPR-based, rapid diagnostic test, nucleic acid rapid diagnostic test for a category A agent. So you can see here, this is work in my lab, a few years ago when Amy Maxson from Nature embedded in our lab and was seeing how this work is done. And you can see the scientists in my lab doing this here. But then I also want to mention the fact that this test is actually way cheaper than PCR. And then you can see the result there. So that you got two bios will give you a positive test, 1 bio will give you a negative test. But then this is the very first nucleic acid CRISPR-based, test for any infectious disease. Well, when we did this, we didn't just stop at doing the detection. So we also realized that when we're in the field, we realized some people get sick. There's some people get very sick of Lassa fever and die, no matter what you do. Some people actually get exposed to the virus. They have the virus in their bloodstream. You test them, they are PCR positive, but then they have no symptoms of the disease and no. The question is that what makes some people sick and others not? So we went on to do the largest genome-wide association study for any category A agent, again, the first largest GWAS for a category A agent or a virus of this nature, and we're able to identify, identify some genes that are actually associated with resistance to Lassa fever, but also some genes that are associated with really poor prognosis for Lassa fever with fatal outcome. So, and then here we're able to come up, we did some functional analysis, and then we're able to determine the mechanisms of invasion and how the virus enter the cell, and then why some people get sick and others don't get sick. So I just want to point out here that the fact that alpha-dystroglycan is the putative receptors of all what adenoviruses, as you see, for instance, here, actually will have to, we definitely have to work with large. Large is another protein that is a human protein, and then this, upside, and then the large and alpha-dystroglycan, joint action is actually responsible of enabling the virus to get into the cell or to block it. So what we observe is that people that do not have Lassa fever, even when they're infected with the virus, they have a mutation at large. And then when the mutated large protein actually binds the alpha-dystroglycan protein, then that prevents the alpha-dystroglycan protein to actually enter the cell and then block, the entry to the cell. And this is a major discovery that we made, and then basically we're pursuing this. You can see here, this was really published, around December 2023, but eventually the paper was out in January or early this year. But basically to show you how you could go beyond just doing sequences, but actually developing countermeasures. So we've been really pursuing this now to see how we can get some monoclonal antibodies to mimic, the effect of the mutated large proteins. So the other thing that I will talk about is how we use metagenomic surveillance to uncover different novel viruses, for instance, and basically is that you're taking people with fevers and then you want to know what is actually driving the fever illness in those people. Take them, run into a sequencer, and then eventually you could use bioinformatic analysis to do that. And then in that process, I just want to point here, this is how we discovered two novel viruses a few years back, the AKV1 standing for epimavirus 1 and epimavirus 2, and then these arabdoviruses, similar to, the Bakongo virus that was responsible for viral epidemic, viral hemorrhagic disease in the DRC in 2012. But then that really actually showing the power behind this. But then this is another use case, for instance, where in Nigeria, around the 2018 November, 179 children died in the Edo state, for a fever of unknown origin or a mysterious disease. The Nigeria Center for Disease Control sent in my lab 22 samples. And in those, we went on to do metagenomics. I could do here at the time we were using the MySeq 4000 or the ISeq 4000, sorry. So to actually do the sequences, but we found that 20 of those samples actually were yellow fever, but then they're all closer together, as you see here in red, and very different from the other Nigerian, yellow fever sample that you see here in purple that have been circulating before. And then this was really brought in by urban transmission. But what is important is the fact that, this particular virus, well characterized, we knew it was different from the ones that have been circulating in Nigeria in the past 94 years. And that really, we made that information available to Nigeria Center for Disease Control. They declared an outbreak, and eventually were able to contain that outbreak, saving thousands of lives. Then this is another case where we talk about, another case of a patient not responding to antibiotics, and then the samples are sent to us, and then we realize that it is a fungi, and in this particular fungi, it's actually the very first, multi-drug resistant Candida auris in our lab, in Nigeria and then West Africa. But then there is a clear demonstration how you could actually integrate, this approach to actually to case management of AMR, for instance. Then the case in scientific report here is a case where we basically had patients that died of two HIV patients that died, and then they were actually having tuberculosis, but then the polygotyping actually showed that it is AMR, but in reality, when we looked at it by next generation sequencing, we realized that it was actually the first cases extensively drug-resistant tuberculosis in Nigeria and West Africa. So, and I just want to point out on the fact that, all this analysis, bioinformatic analysis, all of the things that I told you before are very dependent on bioinformatics. And then in order to do that, you need to have the right platforms in order to analyze the data that are actually coming out of the sequences. So I tasked one of my students, to actually develop a pipeline for analysis. And this is here, Paul, to do that for viruses, while I tasked Ido here actually to do for bacteria. So they were able to create two platforms. One for viral genomic assembly, and then the other one for bacterial genomic, and then using the SNAMEC workflow. And that really is the kind of application that you can download on your laptop. You don't need to have access to internet, but actually can do those analysis on your laptop without having to, to be struggling. So what did we do with all of the knowledge that we acquired? We went on to set up this pandemic preemption response system before COVID-19, and then again, by the time we set up this in 2019 and we're trying to start in 2020, we actually faced our first test. And then COVID actually emerging, first of all, in Africa, or COVID, the first country in Africa to report COVID was Egypt, the second was South Africa, but then the third country in Africa was actually Nigeria. But then the difference between Egypt, Nigeria, and Egypt, South Africa, and Nigeria is the fact that within 48 hours of having the suspected case in Nigeria, we already have the sequence of SARS-CoV-2 gene. So Nigeria then was the first country in Africa actually to sequence SARS-CoV-2 gene. But what we did was not just only to sequence the genome. We knew that this index case was Swedish, was Italian, but actually we demonstrated that actually he got infected in Switzerland and there was no case in country. This is how we've been using the data. We're using the data to actually inform policy in Nigeria. But most importantly is the fact that we use our approach, for instance, our protocol, and share with all countries in Africa, many countries in Africa. And you could see the labs like in South Africa, like Julius and others, to use the same platform and the approach that we use to discover things like Omicron or the beta variant, earlier on. So again, sharing and then providing the capacity and providing the information was important. So we were the second group in the world to determine this particular variant, that is the D614G variant after the groups in the US. But then showing that, we could be at a level where we use science, we could use the surveillance data actually to help, respond to not only locally, but also globally to show how the virus is moving. But within Nigeria, you could see here within time and space, this is how we were showing, the government through the Presidential Steering Committee. You could see here, knowing that how this variant was spreading across the region where we were receiving the sample. But what is important here is actually to say that you could make this actionable. So we knew at some point that Nigeria had 49 different variants circulating in different places in the country. This information was shared with national public health authorities, and then they were using it as a way to respond. And then here you could see the response across space and time, how they could use it as a way to respond to this epidemic. But what we did again was actually to leverage our knowledge of what we call our knowledge of CRISPR, and then to actually create within 8 weeks of that particular of the pandemic, the first CRISPR RDT for COVID. But what is important is the fact that we actually made it power free. So you can see here getting the saliva into the sample, put it into this machine, and then you can get 2 bars that saying that is positive, 1 bar shows a negative. But again, just to show you this is a use case. But what we've done now is actually we've multiplex all these pathogens, and we've created a platform where we can actually multiplex all these tests. Right now, we can actually multiply up to 49 different pathogens in one single test. And then we believe that this is going to be a major game changer, when we actually roll it out, because it's actually undergoing validation. We believe that before the end of the year, before June this year, end of June this year, we'll actually be rolling it out in some few sites in Nigeria. So with this, you don't have to do multiple PCR, but actually just going to do one single test, and then you can actually detect up to 49 different pathogens. But we didn't just do the science, we also perform a lot of training. So we train a lot of scientists across Africa. We've trained over 1,600 Africans. I'm sure, a lot of people in this room would have gone through the ASG training. But most importantly is the fact that, this training didn't just stop across Nigeria. We actually expanded it, across the continent. And then you can see here, we've trained actually 53 out of the 55 African countries. And this has had a huge impact on the way disease surveillance is done on the continent, but it's also the way Africa responded to COVID. You can see here the number of sequences of COVID in 2021, for instance, soaring. And how did they soar? They soared simply because, at the end of 2020, for instance, there were 5,200 sequences. 99% of those 5,200 sequences came between Tulo's lab in South Africa and my lab in Nigeria. But then through the training that we provided, we not only accelerated the number of sequences in Africa, but we also actually gave the opportunity to young Africans to appear into some major journals. 2 science papers that were actually created at the time, to actually show collaboration. So through the work that we did, you can see here, all the different variants discovered both in Nigeria, in South Africa, in Botswana. So actually how they emerge, and then how they spread within Africa and then outside Africa. We use the data also to create, vaccines. And then this is a vaccine antigen design that we actually use with my colleague, Jonathan Heaney in the University of Cambridge, creating, DNA vaccines, but also making sure that, these sequences were very important in terms of, accelerating vaccine development. And then I'm proud to say that, the vaccine that we co-worked on is actually undergoing phase 2 clinical trial in the UK. But we also extended this, for zoonotic surveillance, through our program. So we now have a very strong zoonotic surveillance that is doing both animal environment, but then we learned a lot during COVID. And then these are cases, for instance, where we discovered, the first rabbit hemorrhagic disease in sub-Saharan Africa through metagenomic sequencing, but also, try to understand that, the virus that we thought, which is Lassa fever, for instance, does not circulate only in mastocysts, but also circulate within a large range of hosts that are not only mastocysts, basically providing more insight into how the virus and the epidemiology of virus. But then we also learned that, during COVID, there was what we call reverse zoonosis. That is transmission from human to animals. Basically, in that case, we were infecting a lot of animals with COVID. Our paper here actually showed that when we had a spike or flare-up in human, then we also had flare-up in animals, and vice versa. And when the case came down, then the number of animal cases also came down. We're also looking into bats, do surveillance in bats. That's why we're saying that animals. So one of our graduate students, the postdoc now, George, basically detecting novel alpha and beta coronaviruses in bats. So I'm probably just going to stop with the monkeypox to say that we basically characterize, novel clades of monkeypox. We actually use our platform to pressurize the word to change, the nomenclature of monkeypox, and that's why you hear about mpox, and then you don't hear about the the West African clade or Central African clade, you now have clade 1, clade 2, clade 3, simply because we use our platforms and then our energy to pressurizze the world to change it. So it's a long story, but I don't want to bother you. But then we also characterize the human MPXV1, which is the novel variant that is actually circulating in the global north. So I'll basically just go and say that, we use this platform as a way to use the data from Africa to show that the virus, yes, emerged in Africa, but then the global outbreak in the global north was not from Africa. So, and that the world recognized it. And then we went on to actually characterize transmission just not within Nigeria, but across a range of African countries, and also identify what was responsible for human-to-human transmission. We actually just targeted APOBEC C3 as a target that was responsible to drive that transmission. So, and then we basically, understood the origin. So we knew that this virus actually spilled over from animal to human in 2012, was circulating very critically in human, by 2015. And then, the doubling time was 2 years. And then by 2015 and 2017, we have a flare-up. But then that flare-up really was as a result of critical transmission and then probably not intense surveillance. So in this data, we show clearly that the virus has been circulating for a long time critically, maybe because we're not paying too much attention. But the lesson here is that surveillance has to be intensified, and especially molecular surveillance. But then in closing, I really want to say that when you're doing surveillance, you really do not want to just focus in one country. Look at cross-border. So in this case of MPOX, we're basically showing that, there's a lot of transmission in the eastern part of Nigeria or closer to Cameroon between the two countries, and that really is a lesson that I just want I want you guys to learn. So ultimately what we've done is actually to think about how you could go from setting up something like a very competitive genome sequencing facility, but using the high-fidelity genome sequence data and then, creating the next generation diagnostics, working with the communities in order to refine the diagnostics, and then making sure that at the end of the day, you are creating tools that can actually go, in the outreach center, that is basically in the very remote places and where, that can be most useful. So ultimately, what we've done is actually to expand the scientific capability, of Africans, and then to enable sustainable, independent surveillance for outbreak response on the continent. And really, I just want to say this is just an example of how you could use science in order to change the narrative, and also how to demonstrate the firepower behind the approach that you could use in order to do things in a way that wasn't done before. So I think I want to end up by really thanking all the great minds that have been working with me, all these young folks have been working with me. But again, just to let you know that, they're just great guys, and then they are just like you, and then they could make all these changes happen. So I want to acknowledge our funders, and I want to acknowledge our outstanding partners with whom we work over the years. Thank you.
Thank you, Professor Happy. This is the second time listening to your, actually the third or fourth time, I think it was in Cambridge, and it's usually very interesting to see all what you've done. Some of us in this field, we know how challenging things are, in terms of delivering this. So we're going to open the floor for question. Prof, I know you have just a few minutes, so if you can give us just 10 minutes, because there are very young people here, and as you mentioned, it will be helpful for them, because the idea is to provoke action, basically, and I think that is what AfricaBP aims to do. How do we believe that these things can be done? We have people like yourself who have exemplified that on the continent. So it's now, how do we scale them? How do we get more people on board? So I have 5 questions for you, Prof, and I think there are also a few questions in the chat box. So, and then we can then open up the others. So one of the questions is, how do we prevent brain drain on the continent? When it comes to African genomics, how do we prevent the jackpot stuff you talked about? That's one. Of course, you were at Harvard University. You could have stayed behind. So how do we do that? Then the second is, I was speaking with some colleagues the other day. I think Xavier is on the call here, and I told him, I told Xavier, how that was last year. How do we have more Christian Happies in Africa? And he told me, no, we need to talk about how do we have Christian Happies in the future in Africa. So you need to again try to answer that for us. Then the third thing is, how I know ACGID started as a genomic facility, and I think I've discussed this with you a number of times. But the way I see ACGID now, it can provoke action, it can expand into several areas and provoke help other disciplines. So are there plans to also expand into biodiversity genomics, given that there is an overlap between diseases and biodiversity, especially. The third question is, what would be your top suggestions to young Africans? Half of the people on this call today and on site are actually in the early career of their, and of course, there are also industry professionals here. And the fifth one is, you've demonstrated that genomics can influence policy in Africa. So what are the hurdles you faced? How do we navigate all of this? So I know there are 5 good questions, but if you forget anyone, I'll just remind you, Prof.
Well, I mean, I think I would say, thank God, you need to guide me through the process. So let's start with the first one. I don't have a good brain. So just start with
okay, all right. Okay, the first one is, how do we prevent the Japa syndrome? You were at Harvard University, you would have stayed behind. Well, how do we do that?
Well, I mean, I guess it's first of all, is a personal conviction. So I think, the young ones to know that you cannot succeed anywhere you are. There is nothing that says that, that because you're born in Africa or because you study in Africa, you cannot be a world champion, a global champion. It's all about, your mindset. It's about determining what you want to do, what you want to do, where you want to be, and where you want to do it. And I really want to say that if I were at Harvard, I'm not sure that I would have made the impact that I've made here now, and then transform the number of young people that I've done. 1,600 people, is not given. Again, as you know, thank God, I mean, you know the story. I was at Harvard, but I wasn't fulfilled. I wasn't fulfilled simply because I was training people, but anytime I was hearing stories from Africa, they were negative stories. It made me sad. And I felt that with the knowledge and the skills and the talent that I have, then I actually go back and then help start. And then, by the way, when I was coming back to Africa, I didn't move any lab from Harvard. I didn't take a pin. I came with ideas, and I know that ideas is money. Ideas are money. So, which means that clearly, when you have a good idea, you could package it very well, and eventually apply for a grant. Use that grant as a way to get started. And I started not with a lot of money. I started with a seed grant of $1.28 million, right? And then eventually that grew up to become something really big. But again, it's like, have confidence in believe in what you believe, have confidence in yourself, and go in. Of course, that, it's not easy in Africa. When you go to Africa, I think one of the challenges that we have, or one of the mindset that you should change, especially for those in the diaspora, don't ever go to Africa, to any country, thinking that, you have a red carpet. You should forget about it. You should know that you are going to places where there won't be road, there won't be light, there won't be electricity. You're going to face a lot of challenges. But then the thing is, what is your mindset? Are you prepared to face the challenges? And then in which case, if you are prepared, then nothing's going to send you away. Nothing's going to deter you. So clearly, again, to respond to your question related to the Japa syndrome, I don't think the solution is outside. I think if I were where people are today, I don't think I would have gone to Harvard. Knowing what I see now, I got a colleague of mine, actually, who came from Harvard. I'm still an adjunct professor at the School of Public Health at Harvard, but I got a colleague of mine who came into our lab on Friday. And what she saw there, she was stunned, because she was saying, obviously, you tend to have more facility here in one single place concentrated than the School of Medicine at Harvard, the School of Public Health at Harvard altogether. But then it shows that, a young man these days do not have to go there simply because you have the facilities. Some of us went because we didn't have facilities. Today, there is a platform, right, that the young people can actually use to operate, for instance. And as you know, thank God, there were a few of your colleagues that I brought back from Cambridge. Chinedu, for instance, I brought him back from Cambridge. He's here, and he's operating at a level that is completely different from what he was operating in Cambridge. I have them from Harvard. I have them from Oxford. So they all come. So those are the people that believe in their potential, and then they come. So really, the reality is that it's not always green on the outside or the way people think. But yet the point, the reason why a lot of people go is simply because they don't look around them. There are so many opportunities around us in Africa, and yet we tend not to explore them because our mind is actually outside. There's no way a young African is actually is going to discover the opportunity around him if his mind and his brain is all about, I'm traveling to Canada, I'm traveling to the UK, I'm traveling to the US. Yet, as you are going, the young Chinese are coming to take opportunities. The Lebanese are coming to take opportunities. The people from the US, Europe, they are all coming to take the opportunity. And then for your information, just to say the young people in this audience, if you come to SGID, you're going to see 2 young European. I'm talking about 2 young European, German and then another nationality, coming to our lab for postdoc. I'm not talking about, reversing. That is leaving Europe to come and work in Africa because they've seen a platform where to work. So it's what we're basically doing is actually to change the trend, right? basically proving that, you could get people from expatriate from Europe to come and work in the labs in Africa, and then they are doing very well. So I think basically that's in a nutshell. Believe in yourself and always look around you. The platforms are available. I don't think that we were the way we were 20 years ago, and then there's really no need to actually keep looking outside. Focus, and I'm sure you're going to make the next breakthrough.
Thank you, Prof. Just before I go to the next question, I agree with you on, I have a chat with some of the top centers in genomics in the UK and Europe, and I know what they say about, what you've done, and many of them say this is huge, considering the challenges. So the second question is, how do we create the next Christian Harpers in Africa?
I mean, it's first of all through what you are doing now. Thank God you're creating this, but I think the point is not just, I tell the young people, I charge them, it's not just to attend this workshop. Take knowledge from this workshop, go and then internalize it, digest it, and then start believing in yourself and your capacity and capability. Really, I keep saying, God did not create you stupid. All of you, I think God created you super smart. This is what the discourse I preach every day. You know what? Go and look in. For those that are biblical and those that read the history of science, science was born in Africa. And if science was born in Africa, go and look at the pyramids of Egypt. The pyramids of Egypt were created by and then built by Africa. Now, up to today, they don't understand the physics, the engineering, and then the architecture that actually got into it. That is clear. A continent where you have writing was developed in Africa. A continent where medicine was born. Everything was, physics, astronomy came from here. So the question you should ask yourself is, what happened? How can you suddenly have a group of people that were so smart, that created everything, had the house of civilization, where people like Aristotle and other Socrates and everything came from Europe to learn, and then suddenly they tell you that you're so stupid. I think this is the whole idea, this is the whole thing. Telling us, over the years, product of colonization, that we're not smart. And eventually we end up believing that you're not smart. I want to tell you that you're smart. And I want to tell you that if you believe in yourself, you can create the next vaccine for anything that you want to do. I want to tell you that if you believe in yourself, you could create the next diagnostic for anything that you're interested in, or the next drugs. So this is basically just, the reality. So it's self-belief, self-determination. And then you realize that it's not always about money. It's about actually believing in yourself and your capacity and your capability. It's going to take the time that it's going to take. But if you are resolved and resolute, you'll get there.
Thank you, Prof. So the third question is how ACGID is started off as an infectious disease, and I believe that with what you've done, there is now opportunity to expand beyond infectious, like biodiversity, agriculture, like we're looking at. So do you have plans to kind of look into this area so that you can take that expertise and see how would we apply it in several other disciplines across the continent?
Yeah, as you know, thank God, you're privy to many others, but at least the young people should know that we started a very small lab, 2 rooms. And then from 2 rooms, we went to a small place that had one building that will partition. And from one building that will partition, again, to let you know that you need to grow. And then from one building that will partition, we went to one building that is one center. And then from one building that is center, we now have a whole institute that uses a campus, right? So, but just to let you know, that campus cannot accommodate only infectious disease. So, and that's the reason why, we're morphing into becoming an institute. So you will be hearing about that new name very soon. So, but that institute actually has embarked on the largest or the most ambitious human genomic sequencing program in Africa. We're targeting sequencing 3 million African genomes. And in order to do that, we basically also made sure that actually we invested in getting the most advanced platforms in the world. So basically, we have acquired the NovaSeq X+s. The very first few that Illumina produced in 2023, actually we got the first 2 in Africa. But then the point here is that we are now embarking into non-communicable diseases, but we're also having the possibility. Right now, as I'm talking about, we're actually doing genomic sequencing of insects. We have some of them produced already, some papers from our lab, and now we're also doing what we call a xenosurveillance, basically just to see what, the insect characterize them, and that is part of, fitting very well within the mandate that the AfricaBP is doing, and basically we set up the platform and the foundation for biodiversity genomic sequencing in Africa.
Thank you, Prof. That really connects to what AfricaBP is doing. Then the fourth question is, what are the top 3 suggestions you have for young Africans entering this domain? Because as you probably know, compared to Europe or the US, there are, when it comes to the discipline of genomics, not many of the universities still do this. So what are your top 3 suggestions? Because I actually, again, I had to read some of this from Africa, and then before I got into Cambridge. So now I feel like I, again, have to, contribute to the continent. But what are your top 3 suggestions for the young people?
Well, I think that any workshops like this are good, but I mean, self-education is something that is very important. Again, as you said, you gotta read. And there's a saying that says if you want to hide knowledge from an African, go and put it in a book. But then we need to demystify that by basically just taking the books and read them. We need to read wide, instead of let's spend less time doing social media. Let's spend less time doing Arsenal and Manchester United for the guys, because again, I say that is a recipe for stupidity. I don't see 22 guys running after one round ball. At the end of the day, these guys have millions of pounds every week, and you here, spending the little money that you have in supporting them, going and drinking a beer, buying jerseys, you're actually making them richer, and you're making them poor, you're making yourself poorer. So I guess, you need to focus your energy and then actually just, think about what exactly you want to do. Focus and then really, educate yourself. Then look around for opportunities that can come your way. Because look, success is 2 things. Success is what? Is opportunity that meet readiness or preparedness. Opportunity is a constant. But preparedness is really that thing that is not constant. And you need to understand that if you are not prepared, opportunity will present, you won't be able to leverage it. So I think you got to be prepared by actually equipping yourself with the knowledge and then the skill that is necessary. A lot of these things that you hear about bioinformatics and all these things, they are not rocket science. It's all about, having the interest and once in a while going and try to equip yourself, even personally. Some of us, when I started working, doing bioinformatics in the 90s, it was something that was very virgin. At that time, we didn't have instructors that were teaching you bioinformatics. At the time, we were all going on, and then somebody created a little tool, you go and learn how to use that tool and then try to apply that to some of the things that we were doing. There was nothing like whole genome sequencing. We were doing like, Sanger sequencing, and it was even manual at the time. There was no automatic sequencing. But then you could actually go and play with those things. That's how some of us learn. So you need to actually educate yourself. And a lot of the platforms that are out there, they are actually learning tools, there are tutorials, there are things that you got to do. So I think that is the way you build up, that's the way you grow. And when the opportunity comes, you are more prepared to seize it.
Thank you, Prof. One final question from me before I go to the chat boxes. The biggest problem in genomics is for genomics projects to influence policy. So you've shown through your presentation how you got the world's highest health organization to actually change its name, the name of all of this stigma kind of thing. So how did you do that, and also how were you able to help contribute to influencing policy in Africa, in West Africa, in Nigeria, because we know how challenging it could be, the terrain and things like that?
Man, it's about, first of all, doing research not for the purpose of doing research or publication, but it's actually research for the purpose of public health. If you go and see, for instance, let's take the case of COVID-19. We had the highest genome sequence in Africa. We're actually after South Africa, it's us, in terms of number of genome sequence. But between 2020 and 2023, there was no paper from my lab. So you can see that we were not doing this because we really want a publication. We're doing it, we're helping countries. Mind you, we sequenced samples, supported 38 African countries to sequence their genomes, their SARS-CoV-2 samples. And we made those data actionable. That is basically using the data to show them how they can respond to epidemic. By working very closely with national public health institutions, even if it's local. And when they see that you can use your data and as evidence to make them make the right decision, they believe in you. I can take several cases of countries. I know a country in Africa during COVID-19, for instance, who had a major case, who had the number of cases going up. They didn't know what was really driving the number of cases. They sent sample, we work with the government, we tell them to collect sample across the country. They sent sample to us. Within 5 days, we have gotten the report. And we actually sat down with the Minister for Health and actually the president of that country and showed them why they were having issues. At the time, the beta variant that they had was over the roof. And they will advise them on what to do. Lockdown. That country went on the serious lockdown. And we told them that after 2 weeks, 3 weeks, collect sample, then they were going to review. By the time they collected sample 2 to 3 weeks after, the proportion of beta variant went from 97% to about 16.2%. That they could see that the measure worked. They could see that this is the way to do it. And then eventually they could see that this is the approach to do it. Constant surveillance and then using the data. And when you hear about locking down, it's not that they locked down the whole country. There were some hot pockets that they could actually go there and seal up the place. And that helped, the disease not to spread across borders. So working with national public health is important. Working with regional bodies that are involved in public health is important. So that's the only way, for instance, you're going to use the information to help public health. So the issue that scientists have most of the time is that the primary thing they think about is publication. Of course, publication will come. But if you make publication your priority, then you are missing the point, which is using the data in order to respond to the epidemic. But then when you also have built credibility, for instance, credibility of the data will help you change. The only reason WHO changed at the time is because we used genome sequence data and bioinformatics analysis to prove to them that what was creating the global outbreak of mpox was not was something very different from Europe. And then you remember that before that, it was always that, we have the clade 1 that is what they call the West Central African clade. We have clade 2 who was West African. And then at that time, we seized on the opportunity. Since we said nomenclature has to be done by geography, we asked the WHO and then the rest of the world. So what do we call this one? Let's call it European clade, right? So that it makes sense even. And they didn't want to hear the word European clade, and they will now said, okay, if you can't call it European clade, then you remove the name in all the clade that are circulating. This is how you use it. Also, you leverage your opportunity or your influence to actually do what is right. That is creating equity. And when you get known for actually doing what is right and doing what is good, then I'm sure that, people will tend to believe the data that comes out of you.
Thank you, Prof. I think I've exhausted my question. I'm going to look through the chat box now. Basically, the summary from the chat box, one or two summary. People want to know how they can do internship at ACGID, how they can collaborate with ACGID at the institutional level. And again, I think this is not a question, but more of a comment, just to mention that Prof studied in Africa. I think, Prof, you did your bachelor's and master's. I think someone who knows you from Cameroon just said you were at Ngo Ekele, Alin Nurture. So yeah, Ngo Ekele and UI as well. So just to mention for those who are listening. So Prof, if you can just expand on the collaboration and internship opportunities for the people who are asking, I think that should be our last question.
Yeah, I think we have a very good program, for instance, to get started. Oh, sorry, they're doing some work where I'm here. We have a program, we call it the Genomic Bootcamp, the Summer Genomic Bootcamp, that enables you to come to a lab and then do 2 months of intensive training, and that can help you to acquire the skills. So we do this often in summers, the start of May and then end up around August. We have what we call the foundational track for those people that are not exposed to genomics. And then when you graduate from the foundational track, then you can go to the advanced track, which is basically like a core genomic training program and bioinformatics training program. So we also have some very targeted specific programs. But the thing is, most of the training that we've done that in collaboration with national public health institutions through the Africa CDC. So they choose, because we believe that, you can train both academic, but you can also train people in national public health institutes. So I think we have those different tracks that can enable people from academic and then national public health institution to be trained.
Yeah, thank you, Prof. So let's say if people in the physical meeting have any question. Control, is there a question from the venue? Control? I think there is echo. Control?
I can hear you, just go ahead.
Okay, go ahead.
Thank you very much. Not surprised. I've had it with you somewhere in Seychelles some years ago. With the thing. I want to ask a couple of questions. Do it quick.
Yeah, I think we lost Control. Control, I think there is you are muted. Control. Maybe can you type the question in the chat box if there is an internet issue or control? Kelvin? Let me see if we can, Kelvin. Okay, I think because we need to move ahead, control, we can't get you guys here, and we can also see Kelvin. So if you don't mind, we will just, because I think Prof told me he has a flight to catch. If you don't mind, just send me your question. I will pass it on to Prof, and he can respond via text to me, and then I forward to you. Okay. Thank you, Professor Happy. It's good to have you here, and I'm sure a lot of people are probably inspired. I can see the chat box. And yeah, we hope that you will join us next time. This workshop moves around the continent, as you probably also know. The next one is coming in Nairobi, Kenya, and it will spread across Cameroon, Congo, DR Congo, Tanzania, Uganda, and then the other one is coming in September in South Africa, and then the last one is in November in Morocco, and we're looking at all of North Africa. And yeah, we look forward to for you to join us next time, and also we also look forward to working with you in the future. I must mention that Professor Happy's lab will be participating in the practical session, over the next from Wednesday to Friday. So they'll be doing some Illumina sequencing. Thank you, Prof.
Thank you. Thank God. I just want to say I wish you guys success as you running this program, and then look forward to work with you guys as this program is taking off.
Thank you, Prof.
Bye.
So, yeah, bye. So I think we're going to move to the next item. So do we have the oral presenters? Odrago Wendinda, Ekerete Ibeme. Ekerete Ibeme, please put in the chat box if you're here. Ekerete Ibeme. Ekerete, I think I can see you. I'm going to give you Ekerete, can you unmute? I've just asked you to unmute. Okay, I think we'll probably move to the next presenter. Olorunlaye. Do we have Olorunlaye here? Olorunlaye Ayodeji Taiwo Omotorego to make that presentation. Oral presenter A6. Oral presenter A6. Okay, Coretta is here. So Coretta, I'm gonna give you the speaker, the co-host, right? So you can make your presentation. Please share your screen. You have 10 minutes because we need to move to the next presentation, the next keynote. You have co-host right now, Coretta.
Okay, can you hear me?
Yeah, please speak up a bit.
Can you hear me now?
Yeah.
Okay. Thank you.
Yeah, could you please put it in presenter mode, Coretta? Yeah, Coretta, could you please speak up? We can't hear you.
Okay, can you hear me now?
Yeah, please just keep the mic close to your phone because there are also people in the physical venue who needs to hear you.
Okay. Good afternoon, everybody.
Yeah, go ahead.
Okay. I will be presenting on the result of our findings from mitochondrial DNA.
Sorry, Ekerete, we can't hear you.
Hello, can you hear me better now?
Yeah, we can hear you better now. Plus,
Is it better?
put the voice stuff close to your mouth, so it looks like it's far away from you.
Okay.
Okay, carry on. You have just 10 minutes because we need to move to the next presenter.
Okay. I'm presenting on mitochondrial DNA in tilapia fish. Okay, so this research was we carried out this research as with some group of researchers. So we couldn't attend the workshop physically, so I have to represent the group to make a presentation via virtual means. Thank you for the opportunity. So actually, the need for this research is as a result of the fact that the level of food security has depleted, as we all know, and there are reports that have supported this over the years. And the result of food insecurity actually brings about malnutrition. As you can see on the screen, is our children who are malnourished as a result of inadequate supply of food. And food security can be marginal food security, can be low food security, can be very low food security, where eating pattern within family actually is disrupted. So now the major challenge that we have over the years has been in terms of improving food, has been as the insecurity and the inability of government to regulate fishing, high cost for feed for farmers, and a lot of other challenges. So the question now is, what is the way forward? What can we do as researchers? So we have identified that there's a lot of lack of interest in tilapia fish over the years, and because probably this fish does not really grow that big, but the advantage of the fish is that it doesn't require a lot of inputs in terms of feed, because it can actually do well with feed that normally clarias cannot use for growth and development. So we actually looked at 3 species of this fish: Orochromis niloticus, Aureus, and Mozambicus. We sourced it from 5 rivers in the south side Nigeria, and that included Cross River State, Akwa Ibom, River State, Delta State, and Bayelsa State. So what we simply did was, after sourcing this fish, we had the genomic DNA extraction, and when we targeted the mitochondrial gene, just to be able to see how we can classify the population. We did the target sequencing of the mitochondrial DNA, and using some genomic tools as displayed on the screen. So interestingly, we realized that this species of tilapia that we got from these different rivers were classified into 2 major clades, and the classification was actually based on species. So we have a subclade here, one clade over the left, and then the other clade over the right. And then over here, we realize that the Orochromis mozambicus and Orochromis niloticus were actually grouped together, while Orochromis aureus were on a different clade. So we went ahead to do a mismatch distribution test. Actually, this test is used to test for population expansion within population and between population. So what we realized here was that for each of the species, A here is niloticus, B here is aureus, while C here is mozambicus. We realized that the result generated a multimodal, each of these peak is a mode, generated a multimodal frequencies, indicating that these species have not experienced recent expansion within their within the species. So, and then the AMOVA analysis also revealed that the variation among the species, the variation was higher, percentage variation was higher among population than within population. So we did a demographic expansion test again using the Tajimas and the FUS test. Actually, these are statistical tools that are used to test population expansion activities. And the Tajimas-D results evaluated showed non-significant values. The FUS F test also indicated positive and non-significant values. And then we also try to check these species within each of the 5 rivers that population actually, that we got them from, to what happens within each population. So we realized that the Tajimas-D, that's those tests we did previously for the species, was negative and significant within the population. So this actually is an indication that variation among the species actually exists more within population than between populations. So it's that this is an indication of inbreeding activities within population. And actually, this inbreeding within population may have over the time enable the species to breed through, probably giving a good brood stock within population that can be selected for breeding improvement. Because the fact is that we talk about food security every time. But then for selective breeding purposes, for a successful selective breeding, there must be that understanding of the level of genetic diversity that we have within our various ecosystems. So for tilapia fish, if actually we are to utilize this genetic resource for improvement of food availability, it means first of all, we must understand the genetic stock that we have within our environment. So by our findings, we realize that the tilapia fish within the population that we assessed actually exhibit inbreeding process within their population.
Sorry, you have around 2 minutes. So if you please, you have around 2 minutes.
Okay, I'm summarizing. So this can be tapped. This can be fully tapped in for improvement of tilapia, and then for overall enhancement of food security. So in summary, from the findings put together, the mitochondrial DNA was able to delineate Urochromis niloticus aureus and mozambicus as distinct species of Clarias, and introgression in tilapia are more likely to occur at a higher rate within population than between population. The three species of Urochromis exhibited a convergent relationship over many years of evolving from a possible common ancestral lineage. This convergent evolution is a mechanism that promotes the development of suitable stock through inbreeding, which can be selected and used in outbreeding with other populations for improvement. Thank you. And
thank you, Ekerete. I would like to open the floor for any question. Does anyone have any question for Ekerete? Online participants, do you have any question? You can put your question in the chat box, or you can raise your hand. Online participant, any question? Okay, maybe we can go to control. Control, is there a question for the speaker? So, correct, if you could please stop sharing your screen, that would be great.
Okay.
So, control, do you have any question for Ekerete? If someone is speaking, then you need to unmute. Someone just posted. Okay. Okay, Ekerete, there's a question on the chat box. Why choose mitochondrial DNA? I think that's a question from Ephraim Shimelis. Do you want to respond to that?
Okay, yeah, mitochondrial DNA is actually one of the most utilized part of the genome for determining variation, because the level of variation there is reported to be very high. Okay, and then it is also used in tracing lineage, because we know mitochondrial DNA is transferred through majorly through a particular lineage. All right, so it is much easier to detect variation there that is used for this kind of studies.
Thank you, Ekerete. You also have another question from Juan and Christopher. Can DNA barcoding also achieve same results?
Yeah, definitely.
Okay. Juan, you have your response there. Udo Kachima, thank you for the nice presentation. Can we get a soft copy through the email? So maybe we can share it much later. Adebowale Benjamin, if these species are reared domestically, how is the feedstock economical to Claria pinus? Correct, do you want to respond to that?
I didn't get that.
So it says, if these species are reared domestically, how is the feedstock economical to Claria pinus? So I don't know if it's not clear to you, then maybe you can.
I don't seem to get a question.
Okay,
maybe I'll respond.
Yeah, just respond in the chat.
I'll respond on the chat. Yes.
Yeah.
Let me go to the chat and check. So I'll respond directly to the person.
Okay. Thank you, Ekerete. Do you have any question from control? Physical participants? Any additional from online participants? Before we go to our next keynote speaker, because someone said, although your work is on tilapia, can you perform genetic diversity study on other organisms, example human? So, Ekerete, do you want to respond to that?
On human, I don't work on human. I'm currently also doing some genetic variation studies in Clarias, where I am right now.
All right, thank you. Then control in the physical participants are saying, someone is asking, Aniakan Afia. I don't think this question is for you, Ekerete, but it says, what's the synergy between the first respondent and the genomic team? Are there patent issues with regards to genomics? If they are, what are they? I think this is probably for Christian Happy. What's the cost implication of setting up a lab? So I think we have the genomic companies, they'll be speaking either later today or tomorrow. So please, Aniakan, if you can keep these questions for them, that would be very helpful. So, Ekerete, I think this is for you again. It says, apart from your knowledge, which molecular marker is mostly applied to the fish population diversity? You want to take that on, Ikarete? Okay, I think we lost Ikarete. So thank you very much, Ikarete, for your presentation. We'll move on to the next presenter, which is Dr. Olivia Federigo. Olivia Federigo is with Colossal Biosciences, so I'm not going to talk much. He would introduce himself and so many other things, but he's done quite a lot, particularly when it comes to genomics with the Vertebrate Genome Project, sequencing some species as well. And now he works for a company that wants to de-extinct species. So over to you, Dr. Olivia Federigo, and please do let us know about your presentation. You have, I think you have 30 minutes, please.
Hi, can you hear me?
We can hear you. Please go ahead.
Oh, great. Thank you. Let me share my screen. All right. Good afternoon, everyone. My name is Olivier Federigo, and I serve as the Director of Genomic Resources at Colossal Biosciences. Although I'm unable to join you in person at Port Harcourt, I'm incredibly grateful for the invitation, and I wish I was there. Today, I will share Colossal vision on the extinction, conservation, and what impact on the economy such efforts has. As many of you are probably aware, we find ourselves in the midst of the 6 mass extinction event. Currently, 38% of all species are on the brink of extinction. 50% of all primates are at risk of extinction as well. And with a troubling 20% of all species at risk of extinction, and 50% of them are in decline. But it doesn't stop with animals. In plant life as well is a problem, with a worrying 68% of plant species facing extinction. Unfortunately, this alarming trend shows no sign of slowing down. The number of extinct species is skyrocketing, right, across the tree of life. Approximately 30,000 species face extinction each year, according to similar work by E.O. Wilson. In the US alone, last year, in 2023, 21 known species vanished from our planet forever. 21 just in US. So what can we do about it? So on top of that, the UN declared this year, I believe, that 1 million species are threatened with extinction. And in 2050, about 30% of all species could become extinct, right? So it's kind of a doom scenario, but why do we care? I know that's a provocating question. Beyond our moral obligation to preserve our environments and the intrinsic value of nature, we should care, right? But there are also tangible economic ramifications. Pollution, resource of exploitation, biodiversity loss directly impact human health and the global economy. So we have to keep this in mind. Indeed, several industries rely heavily on the extraction of resources from forests and oceans, as well as on essential ecosystem services like clean water, pollination, and climate stability. According to a study by the UN Principle for Responsible Investment, UNPRI, about more than half of the global GDP, gross domestic production, totaling $44 trillion, are somehow directly or indirectly connected to natural ecosystems. For example, construction materials is about $4 trillion GDP. Agriculture, 2.5 trillion, food and beverage, 1.4 trillion, ecotourism is about $195 billion US dollars, and those energy resources, et cetera, et cetera. BCG, which is the Boston Consulting Group, estimated the annual cost of declining ecosystem amounts to about $5 trillion US dollars a year in the form of lost natural services. So this is not negligible, right? So protecting the ecosystem and make sure the biodiversity is preserved play a crucial role in our economy. So these are not just environmental concerns, but pressing economic issues that we need to address. So biodiversity loss threatens environmental ecosystems, affecting production capacity and disrupting supply chains. Collapsing of ecosystems will drag down businesses, industries, and entire economies. For example, the key role of ecosystem in food security. More than 15% of animal pollinator species are at risk of extinction. So that jeopardizes really seriously our food security. Disease reservoirs. More than 75% of new emerging diseases come from animals, like zoonotic disease, AIDS, Ebola, H1N1, and COVID-19. And is due to ecosystem diversity loss. Right? And also, losing ecosystem will really impede a capability of providing new medicinal innovations, new medicinal solutions. For example, over 25% of all newly approved anti-cancer drugs are related to natural products. So ecosystem is really part of the economy. And in this presentation, what I hope I will be able to convey to you is a strategy as Colossal Biosciences of a strategy of the extinction will be a significant player in helping ecosystems and then economy. But let's first delve into the extinction. What is the extinction? The extinction, according to for Colossal, for us, the extinction of the process of generating an organism that both resemble and is genetically similar to an extinct species by resurrecting its lost lineage of core genes, engineering natural resistances and enhancing adaptability that will allow it to thrive in today's environment of climate change, dwelling resources, disease, and human resources. So the extinction is driving the phenotype, physical characteristics that have been lost to time, making the species thrive more today by improving some features. We can think about drought or cold resistance, or engineering resilience to disease, for example. You can achieve the extinction in multiple ways. You can do by backbreeding, right? You can do by cloning, or you can do by genome editing. And the way Colossal is tackling this problem is by genome editing. That's not all we do. Colossal work in restoring extinct species has many ramifications. To achieve our goal, we are developing an expansive array of tools, techniques, and technologies, and generating data that can be beneficial to conservation and ecosystem restoration. For example, we're developing conservation genetics protocols. We're developing AI, machine learning to track behavior of elephants. We developing a better biobanking system. We developing new way to do assisted reproductive technologies, et cetera, et cetera. So our scope as a company goes beyond just the extinction. And we try to reach out to more fields, and what we produce will help a lot of these different aspects. So again, I'm hoping that with the following slides, I'm going to show you in a couple of minutes, I will be able to convince you that the extinction projects can have a significant impact on the economy. But here, like a very rough overview of our impact. Beyond resurrecting extinct species, we contribute indirectly to protect endangered species, to enhance conservation programs, to rebuild ecosystem, and to provide new technology like software, wetware, and hardware technologies. So all these impacts could be beneficial for conservation and ecosystem. So there are 3 de-extinction projects at Colossal right now. The woolly mammoth project, the Tasmanian tiger or thylacine, and the dodo project, dodo bird. Each project has a dedicated team of researchers. We have about 120 employees at Colossal that is spread out across all these projects. We're still a small company, but we're growing. We have a set of academic partners, and because we cannot do that alone, right? And we have a very clear timeline and scientific milestones to achieve. And I'm happy to say that all the projects right now are on their way to achieve those milestones. Let's start with our first project, the woolly mammoth project. That's probably the one you've heard the most in the media. This project is led by Erina Isoli, head of biological sciences. So it's the first project that Colossal started about 1.5 years, 2 years ago. The woolly mammoth went extinct between 14,000 to 16,000 years ago. Fortunately, we have access to a lot of these samples, and these samples are very viable DNA. So we have a very nice amount of data to be able to do our de-extinction project. But the goal is not to recreate a mammoth identical to those from the past, right? Instead, what we want to do is a mammoth proxy, or more specifically, a cold-resistant elephant with all the core biological traits of the woolly mammoth. I'm going to say that in more details. But what is the motivation, right? Because there must be a goal here. The motivation is the permafrost. So in the last 40 years, temperature in the Arctic have increased 4 times more than the global average. So it's melting very fast. And when permafrost melts, it releases CO2 that was previously sequestered in the soil. And the CO2 being released contributes significantly to the greenhouse effect. So how do we fix this? So the idea behind the mammoth proxy idea is to have these 6-ton giants trample moss, shrubs, and uproot trees to create an ecosystem of grass with no trees. It's counterintuitive, but grass absorbs less sunlight than trees, keeping the great temperature cooler with grass and preventing the risk of CO2. So you can imagine the daily movement of very large mammals across the clear terrain packed down over snow and above the soil, insulating the frozen ground below and helping maintain the permafrost. So that's the main idea behind why do we want to create a mammoth. But this is not just a fairy tale. We can see a glimpse of this effect in the Pleistocene Park in Russia, where they reintroduced, that's an experiment they did, and they reintroduced camels, moose, fur goats, musk oxen, and plains bison, etc., large herbivores. And they look at the soil temperature. inside and outside the park. And what I noticed is that with the introduction of these mega mammals, these large mammals that transform the ecosystem, it reduces the soil temperature by about 8 degrees Celsius. Trust me, it doesn't look impressive, but that's extremely significant. But is that even possible if that when we create the mammoth proxy, if we want to release that in Alaska, in the Arctic, can it sustain such big animal? So we published recently a paper in Scientific Reports where we show that the North Slope of Alaska could theoretically support about 72,000 woolly mammoths. We're a long way before producing 72,000 woolly mammoths, but that means that there is plenty of biomass that will sustain large mammals in Arctic. So this is a rough pipeline for the mammoth, and this kind of pipeline could be is the same for most of the species we're doing. First, we have a sample acquisition, acquire and sequence mammoth samples, generate T2T genomes of Asian elephant or others, identify core genes and identify candidate edits to recapitulate some phenotype of interest. Then we derive cell lines, multiplex editing the genome, and assay those. And when we're ready, we nuclear transfer and fertilize those. And we implant the embryos. So we implant the embryos either in surrogate elephants, but we're also working on some artificial worms, and that will speed up the process quite a bit. But we don't stop here, right? It would be crazy to say Colossal stop their project just here recruiting these animals. There is more to it, right? So we need to be aware of the ethics part of that, the wellness of these animals and the impact on the ecosystem. So for this, we have a lot of zoo partners and conservation partners for rewilding that we closely working with to make sure we do things properly and ethically. So our Distinction Project effort paves the way for a suite of scientific advancement. And this will benefit directly some species, some other animals. And we call them the beneficiary species. And this is not only for mammoth, it's also the other project we have. So in this case, for the mammoth or mammoth proxy, our beneficiary species are forest elephant, savanna elephant, and Asian elephant. They're all going to benefit or are already benefiting from all the technology we're developing around this project, like genome sequencing, multiplex gene editing, assisted reproductive technologies, conservation genetics, biobanking, all these different toolkit we develop as a direct impact on living existing species. So for example, in collaboration with the VGP, the Vertebrate Genomes Project, we generated very high quality genomes of the Asian elephant and African elephant, like 120 megabase and scaffold and 50, so very high quality. We in the process of working on the forest elephant genome and are aiming for T2T genome quality for all these elephants now. We're going to improve that genomes and reach a T2T quality. Another aspect of what we achieved recently is for the first time, we are able to derive iPSCs from elephant cells. iPSCs are induced pluripotent stem cells. So this technology has been well adopted in a lot of mammals, like the northern white rhino. But for some reason, it has been very challenging in elephants to create these iPSCs. And for the first time, we're able to do it. So the way we did it is that we use a two-step process involving chemical media induction, followed by and reprogramming, followed by transcription factor expression, and we modulated the TP53 pathway in order to grow these iPSCs. So why is that significant? Well, iPSCs could be used now for basic research on elephant, right? Before we couldn't do that. We could study cancer. Elephants don't get cancer, so it's a very nice tool that we offer to the community. But also, it gives very new perspectives for genetic rescue in elephants, right? That would be like a crucial tool that will be able to to improve the conservation effort of these animals. A little bit unrelated, but still, we collaborated with Paul Ling at the Baylor College of Medicine to develop vaccines for the elephant endotheliotrophic herpes virus, EHV. In captivity, in human care, EHV is responsible for about 1/3 of all elephant deaths, mostly juveniles, with a 65% fatality rate. So it's a tragedy. But he has been identified as, he has been so far only in captivity, but recently we observed some emerging threats to highly fragmented population of elephants. So things seems to spread, and we need to do something very quickly. So we collaborated with Dr. Ling to develop mRNA vaccine and other kind of approach. And I'm happy to announce that the first vaccine of ESG1A is currently being tested at the Houston Zoo in Texas. So very excited to see how it's going to work out. The second project is the thylacine project, the Tasmanian tiger. So the Tasmanian tiger thylacine went extinct in about 1936, very recently, mainly or 100% due to human cause, right? Hunting and, let's say, use this word, extermination. The thylacine is endemic to Tasmania. And when settlers came in Tasmania and have sheep herds, they were concerned the thylacine will eat all the sheep. So there was a national program that give bounties to people who kill the most thylacine. Sadly, an estimated of 3,500 thylacine were killed through human hunting between 1830 and 1920. So quite sad. So this project is led by Sarah Ord, Director of Space Restoration, in collaboration with Andrew Pask from the Melbourne University. But first, why the thylacine? Well, very similar to our effort with the woolly mammoth, our goal with the thylacine is to be able to restore an ecosystem that is viable, right? The thylacine was an apex predator, and his role was very important to regulate other species population, and without it, his niche hasn't been replaced, and without it, we have the risk of a lot of ecosystem collapse in the region. So why the thylacine again is because, I mean, we can generate a lot of genomes for this project, and we've done that. Endangered azurids, coldernut, devil, numbat, Atechinus, and Phascagelli marsupials. So we're actively working genomics for all these endangered marsupials. We're developing more assisted reproductive technologies for all marsupials and developing exopouch technology so that we can improve assisted reproduction. We plan, and we're doing right now, we engineer our new thylacines and other azurids to be resistant to bufotoxin. So bufotoxin is a toxin produced by the invasive species of the cane toad, and it has been very detrimental to the ecosystem in Australia. And again, the thylacine was an apex predator. His main role was to regulate other populations and to eat the old and the sick, right? Without an apex predator, disease can spread very quickly in other species population. And the dramatic example is the Tasmanian facial tumor disease, and a horrible disease that spread through Tasmanian devils very fast. The third project, the Dodo bird project. This project is led by the amazing Anna Keat. She's the avian species director at Colossal. So the dodo went extinct in 1662 due to human activity and invasive species. Macaque, pigs, rats that destroy the ecosystem or like add eggs. So dodo is endemic to Mauritius Island. It's essentially our flagship project for all of our other avian conservation efforts, right? From this project, we'll be able to build the tools and all the workflow to be able to revive any avian species we want. Its closest relative is a Nicobar pigeon that we're going to use as a surrogate. But how do we make a dodo? So what I'm going to show you here is an example. It's our workflow for the dodo, but it could be applied for all the other birds. It takes advantage of a particular cell type, the primordial germ cells, PGCs, that migrate to the developing gonads in every bird. So very early on in development, these PGC are floating in the blood, and later they differentiate into mature gametes, right? So here in this flow chart, the first step is to extract PGC from the bloodstream from day 2.5 embryos while cells are still in the blood. That would be the Nicobar pigeon. We collect the cells, we grow them so that we have enough to do any edits. We do all the edits we want, including disease alleles, disease resistance alleles or dodo variants. And then we inject back these PGCs into a surrogate embryo. So now the surrogate embryo is going to be a chicken, but a chicken that has been genetically modified so that it doesn't produce his own PGCs. His own PGCs will apoptose, meaning that the only gametes that will be expressed in this chicken once it's grown are dodo gametes, right? So we're going to have these chimeric surrogates raised to adulthood and mated into one another, and they will lay eggs that will contain a dodo. So all this workflow could be applied for many birds. And as I mentioned earlier, in 2023, US alone, 21 species went extinct. Half of them were birds, mostly Hawaii. And they're gone forever. There is no genetic or cell biobanking of them. So it's very crucial that we quickly adopt a new workflow to be able to rescue these species or the next species who have the same problem. We're true believer in partnership with local governments, and we partnership with the Mauritian Wildlife Foundation for the Dodo project. This includes ecosystem restoration efforts. We will remove invasive species for dodo reintroduction in Mauritius. This will benefit other species, right? Because an environment that will be proper for the dodo reintroduction will also be proper for other birds, for instance. Talking about other birds, we started another project with the Mauritian Wildlife Foundation. It's the genetic rescue of the pink pigeon. So the pink pigeon, it's an emblematic pigeon from Mauritius Island, and it's predicted to go extinct in the next 50 to 100 years. It went through a huge population bottleneck, and without intervention, this will be detrimental. So the idea is to be able to use a workflow I described before for you, except that we're going to add back diversity, genomic diversity in the cells to produce more of this pink pigeon before rewilding. We also signed an MOU agreement with the IUCN SSC Pigeon and Dove Specialist Group and its enacted organization, BirdLife International, to collaborate on a number of pigeon conservation projects. And one of the first projects we're working on with them is a tooth-billed pigeon, or called Manumea, from the island of Samoa. We closely working with local officials to rediscover this pigeon. So he hasn't been sighted for about 10 years. So we're co-founding an expedition to find the last of the individuals of these species, and hopefully we should be able to apply a conservation strategy. We're also working on in-situ, ex-situ conservation efforts for the Nicobar pigeon with the same group. So other unrelated, somehow unrelated program we have, but no less exciting, is the Northern White Rhino program. So we are working hand in hand with BioRescue's dedicated national team to employ genetic engineering technologies. So as you know, the Northern White Rhino is technically extinct. Right, there's only 2 individual left, and there are 2 females, and then they cannot get progenies. But fortunately, a lot of the gametes got collected on previously on other individuals that are now deceased. But there was a lot of efforts to do some assisting breeding on these rhino specimens. And our role in this project will be to sequence all the Northern White Rhino historical samples to find the lost genetic diversity, and using our genetic techniques to restore it in the embryo that will be created. Another project is Victorian grassland earless dragon. I promise you that's the last project I'm going to go through. This is a reptile that got extinct in 1969, and we rediscovered a few individuals in 2023. So this is a very beautiful story, and we're collaborating with Zoos Victoria, try to help them to rescue these species to reach a viable population. So we are supporting the establishment of a conservation breeding program at the Melbourne Zoo. They have already laid 50 eggs, so very excited about it, as well as the genomic sequencing of their lost dragons to assist with breeding recommendations. We plan also to generate reference genomes for these species. So we're actively collaborating with them on a lot of the genomic side. But all what I'm describing is not possible without a very good partnership with conservation groups. Especially, we're very happy to collaborate with the Rewild Foundation or the Biorescue Foundation. And this is crucial. We don't want Colossal to be isolated and do the genomic editing, with that to have an awareness of the conservation and ecological impact we can have. And we're working with all these groups to make sure we do things ethically and properly. But to go back to the original question, what is the impact of the distinction? The way Colossal does it, and that's the only company in the world who does it right now, so we wanted to establish a standard. So the distinction can have a direct economic impact, such as ecotourism. It can have indirect impact by creating toolkit that will be used for conservation, that will itself contribute to ecosystem restoration, and then that we have an economic impact. The toolkit also could provide resources and improve medical and biosciences researchers that will have economic impact. So this distinction is an isolated project. It's connected to a lot of things around that make it economically very important. Yeah, so I'm very excited to be part of this company and this very exciting project. And we're looking for partners all the time. So don't hesitate to reach out to me or someone else at Colossal. On this, thank you for your attention, and I'm happy to take any questions.
Oh, thank you, Oliver. Rodrigo, it's nice to see what is happening. I mean, it's so. Do we see a situation where we can have some of this, you know, dinosaurs or something in the zoo, and we can go and look at them? Are we getting there? Right? Are we looking at a Jurassic Park here?
No, it won't be a Jurassic Park, I promise you.
Oh, the Wimble one. Oh, well, I see. Right?
Yeah, this is disappointing, isn't it? But our goal goes beyond that. It's really conservation is one of a big driver for this project.
Yeah, I mean, I see the benefit here because for all of those species that are probably extinct, we could have the opportunity of kind of bringing them back, essentially. So I have 3 questions for you, and then maybe we can go to those on the charts. But I wanted to know with the elephant, the genome, the complete genome sequenced. What combination of genome sequencing platform do you use, and is this also still the VGP? Then when is the earliest that Colossal can get a prototype, you know, that we can see in terms of live species, and how does Colossal aim to scale all of this?
So for the genome question, we use PacBio sequencing long reads, Hi-Fi sequencing, and we add some Hi-C and BioNano on top of that for scaffolding, and it's VGP pipeline. What we're working on right now is to be able to add some ultra-long nanopore to be able to make it T2T. And so we use the same samples now. We're producing right now some nanopore, and hopefully we'll have T2T elephant genomes, which will be really cool.
So we're looking at like a PacBio Hi-Fi plus OmniC, or I think you guys have moved from Hi-C to OmniC now?
Other way, I think it works the same to us. For scaffolding, OmniC or Hi-C gives the same results.
And then for T2, you probably then add ultra-long.
Ultra-long, yeah.
And then so you are looking at 3 combinations here.
Yeah.
Okay, cool. So I think the other question is, when do you guys aim to, I mean, when should we be on the lookout for a prototype? I mean, where can we say, oh, look at this?
It's very hard. It's a question I get all the time about what is the timeline? And I cannot answer it because there is no official timeline, but very soon.
Yeah. So, I mean, and how do you guys aim to scale? Because you talked about some projects, but I think that there are lots and lots of species that have gone extinct. You know, how do you?
So one important step will be to be able to do very serious biobanking, right? While we're scaling up and developing new technology, we don't want to miss some species because they're getting extinct. Biobanking right now is key, and properly biobanking, right? Collecting cells and storing them properly so that we can go back to it and derive RPACs or clone it. I think that's what all the effort needs to be done in biobanking.
Okay, and I think another important point is how all of this will be classified into the ongoing discussions on biodiversity framework. Because let's assume you get a species back. I mean, would that be part of the whole regulatory framework as well? I mean, I think I'm sure it's difficult to discuss or engage at this point, with all of this for most species.
Yeah, sorry, I'm not sure what you mean, but yeah.
Yeah, okay, all right. We're gonna go to the online folks. Do we have any question from the online community? Any question for Oliver? How about from control? Do we have question from control? Kelvin, you want to unmute control? Do we have question from control? Okay, go ahead, please.
Okay, go ahead.
Thank you for this presentation. As I said, I moved from a consumer of bushmeat to a conserver of species. My question is simple. Can we have a situation where we can repopulate our zoos or have some reserve where we can repopulate the extinct species there? Thank you.
I'm sorry, I couldn't hear very well.
Did you catch that, Oliver?
No, I didn't catch that. Can you repeat that?
Could you please repeat the question? We didn't catch. There's some like background noise. Could you please repeat that?
I'll put it in the chat. I will answer
Yeah, the question was, well, we part of the world we normally consume also future generations. Thank you.
I think I to be honest, I was a bit I find it difficult to also hear the question. So is there a chance that control can put it in the chat box? There's like echo on the background. And we sorry? So yeah, if you could please put this particular question on the chat box.
Chance of repopulating our zoos with extinct.
All right, Oliver, she's asking rather the same question I asked. Are we looking at a what's it called? A Jurassic Park here?
Yeah, my answer is still the same. Probably not. That's not the goal here. Now, this animal will be in zoos for a little bit until we reach a population size we can rewild, right? We cannot just rewild one organism. We have to rewild like several individuals in the population. So there'll be some in captivity for a bit.
Okay.
So I don't know if, but not Jurassic Park.
So you don't think, according to our question, you don't think we can repopulate our zoos, with species that has gone extinct? I mean,
that would be a question for higher ups at Colossal. I can't really comment on that.
All right, I understand. Okay, do we have any other question for Oliver Federico? Online community, on-site community, the physical participant? Any question from the venue? Control. Any more question? Control. Control, you need to unmute. Control, you need to unmute, please. So control main, you need to unmute. We can't hear you if you're asking. Okay, now you've unmuted, but we can also hear the.
So to quickly answer the question, can we repopulate a zoo of extinct species? Yes, but that's not the goal, right? The ultimate goal is to rewild those extinct species.
Oh, right.
If the niche ecosystem is still there and the niche is not taken, the goal is to rewild it, not to put in zoos.
Okay, I mean, it's nice to hear from you, Olivia. I have also asked Anne to get in touch with you to see you could also be invited to the workshop in August. So Anne is here, so I'm sure she's here. She'll probably be in touch with you.
All right.
So if there are no more questions from control and in-person participants, we would thank you very much, Dr. Olivia. We would go have a short break, maybe for I think what's the time now? I think we should be back. Should be back in the next 45 minutes so that we can just go through the oral presentation and close for the day. Control? Can we be back for the next 45 minutes? Okay. All right, we'll see us all in the next 45 minutes, and then so that would be okay, shall we say around 4:30? Let's be back at 4:30. So we'll see us all at 4:30 to wrap up for the day. Thank you. 4:30 UK time, Nigerian time or West African time, GMT +1.
Yeah, break now. 45 minutes break is really long. I don't know if it came up. I used power bank to plug in. Okay, so we just 5 minutes. I don't know if it came up.
Our session has ended. Thank you, the big man and the big woman. I hope we meet today. What do you call
And this one of it. And this one of it. Try this. I use answer.
No, not the answer.
The phone type.
you say that
Hello, I can hear you.
Now, as you mute all three, you the rights to mute and unmute for all three. Check whether all three now have
To host all of us. It will just appear here.
That's what I'm saying. Check whether you are still host.
Not yet. Not yet.
So what they are saying,
Okay, he has done that.
I can hardly hear you, but we have seen that you have now given the all the
I've been there now.
controls.
Control is
Please control.
Maybe can you
He has
use
made
your
co-host.
please can you call
all three?
I think you are using this one. You are using this Wi-Fi.
Yeah.
Yeah.
Okay,
From your phone.
can you okay, you don't have his number, but you can call him from there. No.
I can't call from him.
You can log into this now.
He's online. But he's not talking to us online. Try chatting with him.
Can't you write to
That
him
has to be
personally?
public.
No, the
No,
private
private
chatting.
Use them here.
Okay.
Or you connect me to this internet.
Okay, that's what we're coming very well.
Because
They
it's
share
like
the hotspot.
Welcome, everyone. So I think we're going to start like in 2 minutes. Control, I think there is no sound in the control center main.
It's saying no sound. And this audio is also going on.
Control center main, there's no sound. Okay, I think we'll start in 1 minute, so we can be able to finish up in the next half an hour or so.
Okay. Say something.
There is echo on the background. There is echo on the background. Okay, thanks everyone for coming to the final part of the workshop. We have just 3 more presenters. Actually, yeah, 2 to 3 more presenters remaining. I think we would then finish off for today and return back tomorrow. So I'm just going to call on Cindy Feleke. Are you here? Cindy Feleke, are you here?
You mute me now. Hello, can you hear me, sir?
Yeah, we can hear you.
Okay. So is the whole bag still there? So is the whole bag still there?
No, it's not.
Okay, he said no. Yeah. Okay. Can you hear us now, sir?
No, we can't hear you. Sorry, we need to move ahead. We need to wrap up in 30 minutes. So you can resolve.
Okay, let's speak. Let's know if when we use the mic, if it will.
Yeah, all right. Okay, do we have Cindy Feleke on the call today? Just put in the chat box if you're on the call so we can have your presentation. How about Haptamu Goshu? Haptamu Goshu, are you on the call? Haptamu. And the panel presenter, Osoji Odogu Ezebiro, oral presenter A9. Are you on the call? Oral presenter A9. Victor Ezebiro Odogu Blessing Osoji. Victor, are you presenting or who is presenting? Do we have Blessing Odogu or Victor Ezebiro or Julian Osiji or representative A9? Because I know I've seen them on the call. We have just 3 presenters, and it looks like the 2 of them are not around. Okay, how about Taiwo Crosby? Taiwo Crosby or Motoriogo? Sorry, Victor, you can't present tomorrow because other people will be presenting. So we'll have to skip you. And try to see if we can have a slot for Taiwo.
Thank God. Still, I think the student who is to present this is not available. Is it?
Okay.
Wait. Yeah.
Yeah, I think in that case, then I think we'll probably come to the end of the meeting today, since you're not available, and we'll carry on tomorrow. We'll start with the commercialization session rather. Okay, thank you all for coming. I don't know if Julian wants to say anything before we wrap up, or anyone in the control. Otherwise, thank you all for coming, and we'll see you all tomorrow at what time does it start tomorrow? Yeah, it starts at 9 o'clock GMT +1 tomorrow. And also thank you to all the speakers who did speak earlier today, and the oral presenters as well. See you tomorrow. Bye.